Okay, very good. So then we have a privilege to have a lecture by Cynthia Vinzant, who is a professor at the University of Washington. He's going to tell us about log-concavity.
Great, thank you very much. Please let me know if you have any trouble hearing me or seeing. Okay, great. So thank you very much for the invitation to speak at FIPSAC. It's a real honor. I'm going to be talking about some work on a class of polynomials that were mentioned yesterday and a connection to combinatorial objects called matroids and something called expanders. Let's see if this works. And I should say this is based on joint works with Nima Anari, Kuikui Liu, Shayan, Oveis, Gharan, and Thuy, Vuong. Okay. And so eventually what I want to do is talk about a class of multivariate polynomials with real non-negative coefficients and how we can learn about combinatorial objects through them. But I want to do a warm-up, which is just univariate real-rooted polynomials, which are well known and loved in combinatorics. So it's going to be a polynomial in one variable, and I'm going to be interested in the property that all of its roots are real. So all the imaginary parts are 0. And these class of polynomials have lots of nice properties. In particular, if a univariate polynomial is real rooted and has non-negative coefficients, then its coefficients actually have to be they inherit a certain discrete log-concavity property known as ultra-log-concavity. And this is also called Newton's inequalities. So you take the coefficient of, so if ak is the coefficient of x to the k, and you divide each coefficient by n choose, the kth coefficient by n choose k, then what you get is that these coefficients scaled by the binomial coefficients are log-concave in this way. They satisfy the following binomial inequalities. And the easiest case is just n equals 2, where this is just the fact that the discriminant of a quadratic polynomial has to be non-negative. And the other ones are basically derived from that quadratic discriminant. Another nice property that they have is they also have satisfy a functional log-concavity, which is if you have a univariate polynomial that's real rooted with non-negative coefficients, then as a function on the positive real line, it is log-concave. So here I have a nice univariate polynomial factored out in terms of its roots. And if I take the second derivative of its log, so I can test concavity of its log, what I get is a rational function that's non-negative, non-positive everywhere it's defined. And so above all of its roots, this function log of f is going to be concave. So already from this property about the roots of polynomials, we get two interesting flavors of log-concavity. We get log-concavity on the coefficients of the polynomial, and we also get log-concavity of f as a function on the positive real line. There's actually multivariate generalizations of this. The nicest I think of is something called stability, which is if you have a multivariate polynomial now, we'll call it stable if it has no zeros in the product of the upper half plane. So it has no zeros, all of whose imaginary parts are strictly positive. I'll leave you to convince yourself that this is a generalization of real rootedness. There's lots of nice ways to get these. You can take the determinant of a linear matrix where the coefficient of every variable is a positive semi-definite matrix. And since it's a combinatorics audience, maybe one of the nicest examples, which you can actually derive from this using the matrix tree theorem, is just the sum over all spanning trees of a graph times the monomial, which is the product of the edges indexed by that spanning tree. So for example, here I have a graph with 5 edges. There's some collection of spanning trees of this graph, each of which I turn into a monomial, and I sum them all up. And this can be written as a nice determinant. And so we see that this polynomial, cubic polynomial in 5 variables, has this property of stability. there's lots of, so stable polynomials show up in lots of interesting ways in combinatorics and optimization. You can check that they also have this continuous log-concavity property. And this has been used in what's called hyperbolic programming and convex optimization. They were integral in the proof of Caddis and Singer's conjecture and operator theory by Marcus Spielmann and Srivastava. And they've also appeared in algorithms for counting and sampling from discrete probability distributions. And in particular, there's a beautiful survey on negative dependence in discrete probability distribution and the geometry of polynomials. In particular, so one theorem proved by Peter van den in 2007 was that if you have a multivariate polynomial with this property of stability, then a different polynomial you can derive from it is non-negative on all of r to the n. And if you evaluate this new polynomial at a particular point, it will still be non-negative because it's non-negative at every point. And this then tells you something about the discrete probability distribution given by the coefficients of f. So for example, if the coefficients of f index the probability of a certain subset appearing, then evaluating this polynomial at the all at once vector tells you something about the probabilities of particular elements showing up in your randomly generated subset of 1 through n. For example, if I take a spanning tree of this graph with 5 edges uniformly at random, so all of the 8 spanning trees show up with equal probability, then I could ask about the probabilities that my favorite edges 1 and 2, show up in this spanning tree. And you can check that the probability that both show up in this spanning tree is they show up in both in 2 out of the 8, and versus the product of the probabilities that they each individually show up. And this inequality says that if I want both to show up, then the probability will be less than if these are independent events. And so this is called negative dependence. So on a high level, what we can say is that if the generating polynomial of some distribution is stable, its roots avoid some region in the complex plane, then this does something interesting about this discrete probability distribution. This class of polynomials is also known to be sort of closely connected with combinatorial objects called matroids. I know that many of you in the audience will be familiar with matroids, but I wanted to do at least a quick crash course or reminder for those who are not. We also saw a nice definition in Vuong's talk yesterday. But so on a high level, matroids are a combinatorial model of independence. This captures linear independence of vectors in some vector space. It also captures cyclic independence of edges in a graph. Formally, we can encode a matroid as having a ground set, which is the numbers 1 through n, and some non-empty collection of subsets of n with an exchange property that if I have any 2 subsets and I pick any element that's in one but not the other, I can find an element, say little b and big B, to trade it out and get back to something in my collection. There's lots of reasons to love matroids. One is that these are the objects on which the greedy algorithms always succeeds in finding an optimal set. For example, finding the minimum cost spanning tree in a graph. And there's many nice encodings of matroids. One way of encoding a matroid is this collection of bases that I've written down. Another is through its independence complex, which is a simplicial complex I get from just taking an abstract simplicial complex, from just taking all of the subsets of 1 through n that are contained in some basis, some element of curly B. And then another nice combinatorial object to associate to a matroid is the 0, 1 polytope that I get by taking the convex hull of the indicator vectors of all of these bases. And in fact, there's equivalent definitions of matroids using all of these different types of objects. And in particular, my favorite non-example of a matroid is the following collection of subsets of 1 through 4. And I leave you to check that this does not satisfy this axiom. And as mentioned in Suihong's talk yesterday, there's a lot of developments in the theory of matroids in the last couple years, many of which really starting with this paper from 2015 by Ediprisito, Hu, and Katz, who developed combinatorial Hodge theory in order to study matroids. So they associate large commutative rings to these combinatorial objects in order to better understand them. And in particular, use it to show log-concavity of certain sequences associated to matroids. For example, if I record the number of independent sets, so the face numbers of this simplicial complex that I wrote down before, then this sequence is log-concave for any matroid. And they do this by proving some theorems, a Hard-Lefschetz theorem and a Hodge-Riemann relations for a commutative ring, a large commutative ring associated to this matroid. And this inspired a lot of work by many people. This is an abridged list of the many people who have sort of continued on this work. And in particular, the one that is most closely related to this talk is the work by Peter Bendun and Jun He on Lorentzian polynomials. And in fact, the class of polynomials that I'm about to introduce ends up coinciding with the class of polynomials called Lorentzian polynomials. And so what happened is many authors ended up converging on the same types of objects. And the common theme in all of these works were signatures of quadratic forms on certain subspaces. This is sort of the important part, or one of the most useful parts about the Hodge-Riemann relations, and shows up in the definition of Lorentzian polynomials and will sort of secretly show up in the definition of polynomials I'm about to talk about. Any questions so far? You happy with this? Okay. So the class of polynomials that I want to talk about are ones where we just demand log-concavity as a function from the get-go. So I'm going to call a polynomial log-concave on the positive orthant if it is as a function. So f should be positive on the positive orthant, and when I compose with log, I should get something concave. And this is really equivalent just to the condition that the Hessian of log of f is negative semi-definite when I evaluate at any point in the positive orthant. And in fact, so stable polynomials, this generalization of real-rooted polynomials whose coefficients are non-negative, immediately have this property by a generalization of the real-rootedness calculation for univariate polynomials. So in particular, the generating function of the spanning trees of any graph have this property, are log-concave on the positive orthant. And Gurvitz in 2008 showed that the log-concavity of f and all of its derivatives in fact imply Newton's inequalities on the coefficients for univariate polynomials with this property, or bivariate homogeneous polynomials. So the idea of which is you can recover Newton's inequalities from log-concavity. And in fact, so along with my collaborators, we showed that using the ideas of combinatorial Hodge theory, we showed that if you take the basis generating polynomial of any matroid, so to every basis, you associate a monomial and then sum them all up with coefficients 1, that this polynomial is log-concave as a function on the positive orthant. And as I mentioned, so Peter Brandon and Junhe develop an equivalent notion of Lorentzian polynomials and show the connection with matroids and also M-convex functions, which is a sort of souped up version of matroids. Okay. And as I mentioned, so log concavity of a polynomial is secretly all about the second largest eigenvalue of some real symmetric matrices. And in particular, we can just do this, we can do out this calculation. A polynomial is log concave at some point in the positive orthant. What does this mean? This means that the Hessian of log of f evaluated at this point is negative semi-definite. So all of its eigenvalues are less than or equal to 0. And if we actually do out the multivariable calculus exercise, we see that the Hessian of log of f is f times the Hessian of f minus the gradient times its transpose, all divided by f squared. And so what this is when we evaluate at some point is a constant times a symmetric matrix minus a rank 1 symmetric matrix. And we want this to be negative semi-definite. It's not too hard to see that this implies that the Hessian of f, not the log of f, but the Hessian of f actually has to be negative semi-definite on the hyperplane orthogonal to the gradient. And so this means that the quadratic form given by the Hessian at this point is non-positive on some hyperplane, namely the hyperplane of points orthogonal to the gradient evaluated at whatever a is. So here's a picture of a hyperplane and a quadratic form that's positive in some region and negative on this blue hyperplane. And you can see that this means that this defining symmetric matrix has to have at most one positive eigenvalue. And in particular, if the polynomial f you started with has non-negative coefficients, and then you take its Hessian, and then you evaluate at a point in the positive orthant, then all of the entries of this Hessian are just going to be derivatives of f evaluated at a positive point. And so in particular, they're going to be non-negative. And so if you have a symmetric matrix, all of whose entries are non-negative, then it also has to have at least one positive eigenvalue. And so altogether, this means that the Hessian of f evaluated at some point, the second largest eigenvalue can be at most to 0. There's at most one positive one, and all of the rest of them have to be less than or equal to 0. Just as an example, here's the basis generating polynomial for the uniform matroid of rank 2 on 4 elements, just the elementary symmetric polynomial. If I take the Hessian of this polynomial, it's just a quadratic, so I get a constant matrix. I don't need to evaluate it at any point. And this is a rank 1 matrix minus the identity matrix. And you can check that this has one positive eigenvalue corresponding to the eigenvector of the all ones, and then all of the rest are, all the other eigenvalues are negative. So in particular, if we have, so this is just summing up what we had before. If we have a homogeneous polynomial of degree at least 2 with non-negative coefficients, then being log concave at some point is the same as the Hessian at that point having at most one positive eigenvalue. And from this condition of functional log concavity, you actually recover some conditions for discrete log concavity. So in particular, if f and all of its derivatives are log concave, so I forgot to define strongly, but strongly log concave is this f and all of its derivatives are log concave on the positive orthant, then you recover that the sequence of coefficients is ultra log concave. And the proof is similar to the proof of Newton's inequalities. If you take the enough derivatives of f to get down to a polynomial of degree 2, then you can take the determinant of the 2 by 2 matrix, which is its Hessian. And this 2 by 2 matrix should have one positive eigenvalue and one negative eigenvalue. And so in particular, its determinant should be less than or equal to 0. And if you actually do out that calculation, what you get is exactly the condition that on the three consecutive coefficients, k minus 1, k plus 1 of log concavity. And so the theorem is that, in fact, these correspond very closely to matroids. If you have a polynomial that's strongly log concave, so log concave on the positive orthant and all of its derivatives are log concave on the positive orthant, then the monomials that show up have to be the bases of a matroid. And moreover, any matroid shows up this way. So if you take any matroid with bases B, then the generating polynomial for the bases of this matroid are log concave, as is the sort of homogenized generating polynomial for its independent sets. And here's the same example again. And just to check, so if we take a non-example of the bases of a matroid and we take its Hessian, in fact, we get a symmetric matrix that's block diagonal and has two positive eigenvalues, and so this polynomial is not strongly log concave on the positive orthant. And so one consequence of this is Mason's conjecture that the sequence of sizes of independent sets is ultra log concave. This is what Thuy talked about yesterday. In fact, a generalization of this is what Thuy talked about yesterday. And one can derive this from the statement, from the log concavity of the polynomial in n+1 variables on the slide before, just through restriction. So we have a multivariate polynomial that's log concave, and one can show that if you restrict some variables to be equal to each other, so that you're summing up over all of the independent sets of y to n minus the size and x to the size, that this will also be log concave, and this is exactly a bivariate log concave polynomial whose coefficients are what we want. So just as an example, if I take my original graph with five edges, and I look at all of the independent sets of this matroid, which are all of the acyclic subgraphs, I can organize them by their number of edges and count the number of each. And if I divide by the corresponding binomial coefficients, I'll get some sequence that will, and the guarantee is this will be log concave. And the reason is that the corresponding bivariate homogeneous polynomial is strongly log concave on the positive orthant in R2. Okay. Let's see. So I might skip through this a little quickly, but I wanted to give at least a flavor of some of the technical machinery hiding behind this. Let's skip through most of this. A high level idea of the technical content is this property of being strongly log concave. There's many equivalent ways of writing it down. And the most important thing is that one can test this property of being strongly log concave, which hopefully seems like a difficult thing to test. You have a matrix with polynomial entries, and you have to check that its evaluation at every point has some signature. That one can actually test this through some combinatorial condition on the coefficients and the log concavity of just all of its quadratic derivatives. So if you take derivatives down to a quadratic polynomial, so that whose Hessian is now just a matrix, that these finitely many quadratic polynomials are all log concave. And a rough idea is that one can inductively understand log concavity of a homogeneous polynomial through taking convex combinations of Hessians of its derivatives. And this is similar to what we saw in Thuy work that he presented yesterday, where you want to understand some large object. So for example, the log concavity of some large polynomial large degree in n variables. And one can reduce it through some combinatorics and some convexity to the log concavity of much smaller pieces, to many smaller pieces. Okay. And so what we're going to see is actually this property has shown up in other places in the literature, and also in some recent work on Markov chains. So what I'm going to do is I'm going to sort of take a right turn and tell you about some applications of this theory to sampling problems involving Matroids, where the second eigenvalue of these Hessians will also play a large role. So if you've spaced out, now's a good time to come back in. And so very broadly speaking, just as motivation, there's many ways in which the second eigenvalue of a real symmetric matrix, it tells you many important things. One important thing that second eigenvalues can tell you about are expansions of graphs. So if I have a graph on n vertices with some edges, I can look at the expansion of some subset, which is the number of edges between the subset and its complement, divided by the smallest size of this. And if I look for bottlenecks in a graph, I will take the minimum overall subsets of this quantity. And it's well known by Cheever's inequality that if I had a regular graph, that this value, the expansion of a graph, can be bounded in terms of the second eigenvalue of its adjacency matrix. One conjecture that we'll come back to is in fact that the edge graph of any 0, 1 polytope is conjectured to have expansion at least 1. And we may come back to this and for polytopes that relate to matroids. There's many reasons one might want expansion to have things sort of spread quickly, or maybe if it's for diseases, maybe you want to have small expansion, you want things to spread slowly. But a closely related concept is sort of mixing times in Markov chains. So if you have a Markov chain given by some transition matrix, here's a small example, and with some stationary distribution, with some details that I'm maybe leaving off, you could be interested in its mixing time. How quickly does any place that you start converge to this stationary distribution? Let's assume that it's unique and that everything converges to it. And under some conditions, this time, the mixing time, can also be bounded in terms of essentially the second eigenvalue of this matrix, or more formally, the largest eigenvalue in absolute value, besides for the top one. So what I want to tie this into is some work on a Markov chain that happens on faces of a large simplicial complex that mixes quickly. So these are called high dimensional expanders, and this builds on a long line of work by Dunur, Garland, Kaufman, Lubotsky, Mass, Oppenheim, and many others. So if you start with a simplicial complex that's pure of some dimension, so all of the maximal subsets that appear have the same size, I'm going to define the following random walk on faces between faces of k elements and faces with k-1 elements. And it's the following. If I take some element with k, some face of the simplicial complex with k elements, then I can get a face of size 1 less by uniformly throwing away some element. For example, here I have some collection of 4 out of 7 elements, and I throw away the middle one, and now I have 3 elements. And similarly, if I start with something with k-1 elements, I can add one in with some probability to be specified later. And I could do this as long as I want, and this defines a random walk. And in particular, if I take 2 steps in this random walk starting from the top, then this gives me a random walk on the elements of size k. And if I take 2 steps of this random walk starting from the bottom, then this gives a random walk on subsets of size k minus 1. And these are usually called the down-up walk and the up-down walk. And they have some transition matrices, some potentially very large transition matrices you get from these random walks. And so if you want to understand, for example, mixing time of this process, one would want to understand, for example, the second largest eigenvalues of these potentially quite large matrices. And there's many different ways to study this, but in particular, some work by Kaufman and Oppenheim, they bound the eigenvalues for these random walks in terms of the eigenvalues of random walks on small pieces of this simplicial complex, namely small links of this simplicial complex. And they call, if you can bound eigenvalues in terms on walks on the links, then they call these lambda local spectral expanders. Local because you're bounding things on local pieces, spectral because you're doing it in terms of the eigenvalues. And so they developed this beautiful theory about that uses sort of local pieces of information to tell you something about a large random walk on all this holdings. And so what I show with my collaborators is that in fact, the independence complex of any matroid is a 0 local spectral expander, whatever that means, satisfies the conditions that are involved in this theorem. And in particular, there's many consequences of this that I'll try and describe if there's time. But in particular, the edge graph of the matrix basis polytope has edge expansion at least 1. Yeah. I can give you a high level answer. So there's some small, so what they do, so lambda is a bound on the eigenvalues that happen within the links. And then the eigenvalue for example, these much larger transition matrices is some function of this lambda. Yeah, that's mostly true. Okay, so just for a very small example, we could define the following random process on subsets of 1 through 4 between subsets of size 1 and subsets of size 2. Okay, so if you hand me a subset of size 1, I'm going to add an element uniformly at random of the ones that are missing. So I'm going to add any given element with probability 1/3. And if you hand me a subset of size 2, I'm going to remove one of its elements uniformly at random. So there's 2 elements, so I'll remove each of them with probability 1/2. Okay. So this gives a random walk on this graph. And if I start at a subset of size 1 and take 2 steps, this defines 1 step in a Markov chain on this bottom row. And here's the transition matrix for this Markov chain. I have a 1/2 chance of starting somewhere, adding something, and then removing it again. And I have a 1/6 chance of adding something and removing the other thing. And I want to point out 2 nice things about this matrix. One nice thing about this matrix is, in fact, it's positive semi-definite. Because you're composing sort of a matrix and its transpose. You're taking 2 steps in a random walk on a bipartite graph. So in fact, you can write this as a matrix times its transpose, so it's positive semi-definite. All of its eigenvalues are non-negative. And the other sort of notable feature of this graph is that it is 1/2 times the identity matrix plus a 6 times the Hessian of this polynomial, the uniform, the elementary symmetric polynomial of degree 2 and 4 variables. And in particular, this polynomial is log-concave. And so we know that the second largest eigenvalue of this piece is at most 0, which means that the second largest eigenvalue of this matrix is at most 1/2. And so then this tells us together, these two pieces tells us that the smallest eigenvalue is actually non-negative, and that the second largest eigenvalue is at most a half. And so then the important eigenvalue for the mixing time of this random process is at most a half. And in particular, in order for a random walk to mix quickly, you want this to be far away from 1. And 1/2 is sort of good enough, is far enough away from 1. Okay. And then the other, so we're not done with this example. We're going to milk this example for all it's worth. So this is the random walk that we get from starting at the bottom, going up, and then going down. The other thing I could have done is start at the top, subsets of size 2, go down and then go up. This is going to give me a random walk on these 6 elements. And now we're going to have we're going to have a 6x6 transition matrix. And in fact, because again, we're taking 2 steps in a bipartite graph, again, this matrix is going to be positive semi-definite. And in fact, we're just taking basically the same matrices we had on the slide before, say A transpose, and doing A transpose A. So not only is this positive semi-definite, but it will have the same non-zero eigenvalues as the 4x4 matrix on the slide before. And so in particular, the important eigenvalue for the mixing time of this random walk is the same as 1/2. And hopefully this at least gives a flavor of the computations involved. This is sort of one piece of this induction in understanding Markov chains. You can imagine that I took 4 is slightly smaller than 6. I understood a random walk on 4 things, and then using the fact that I'm taking sort of 2 steps in a bipartite graph, used it to understand the mixing time of the random walk on this piece. So I can imagine going up some post set and understanding random walks on larger and larger elements. And so this is really what they do. So formally, we'll call, if we start with a simplicial complex with some weighting that I don't want to get into, we'll call it a 0 local spectral expander. We're in the weeds now. So if the one skeleton of all of its links are connected, I apologize for not defining what a link is, but if some combinatorial condition holds, which is the connectivity of some graphs, and also that if I take links of large faces, that the transition probabilities of the corresponding sort of induced random walks have eigenvalue at most a half. So high level, some combinatorial condition plus some bounds on the eigenvalues of what happens in some local pieces. And precisely what they show is that if you have a 0 local spectral expander, that the second eigenvalue of this very large transition probability on potentially like n choose d things is bounded away from 1 by 1 over d. So you get a spectral gap of 1 over d. And the idea is similar to this, what happened in this small example, is that one can relate the eigenvalues of random walks between different levels. And using sort of connectivity and this bound on the eigenvalue, you can in fact keep going up. You can keep going up in this post set. You can relate eigenvalues of starting at k elements and going up and then down. Can bound these eigenvalues as a function of the eigenvalues you get from going down and then up. And so this lets you sort of inductively work your way up this entire post set from very tiny pieces to large random walks. And so the way that I understand this, or that my co-authors and I understand this, is by translating all of these things to polynomials. So if you hand me a simplicial complex, possibly with weights on the maximal faces, I will immediately write down the generating polynomial. If this is a simplicial complex on n elements, then I will write down a generating polynomial in n variables corresponding to this. For example, here's a simplicial complex on 5 elements and the corresponding polynomial. And then all of the data that was asked for in this theory of high-dimensional expanders, one can actually think of in terms of polynomial operations. For example, you can convince yourselves that taking lengths of certain faces algebraically corresponds to taking derivatives with respect to the corresponding sets of variables. This connectivity condition corresponds to some other connectivity condition. And as we saw in this small example, the transition matrices for the eigenvalues on these links, these small local pieces, actually one can write down in terms of the Hessians of derivatives of the polynomial. So this is not meant to be super well understood, but just to give a flavor of what's involved. But in particular, this bound that was asked for in the Kaufman-Oppenheim theorem really comes from the second eigenvalues of Hessians of derivatives being non-negative, non-positive. And so in particular, the condition for being a zero local spectral expander, whatever that is, actually turns out to be exactly the same as a certain polynomial being strongly log-concave on the positive orthant. We're doing a time. We're doing okay. So some consequences of this, I already mentioned some, but in particular, since matroid, the generating polynomial for the basis of any matroid has this property, then the down-up walk on the bases of a matroid mixes quickly. In particular, if you go through the translations of the eigenvalues and the theory I gave you before, it'll mix on the order of r squared log n, where r is the rank of the matroid and n is the size of the ground set. This has been improved since then, in particular by Krain, Go, and Musa, using a modified log Sobolev inequality, and myself and my co-authors. And so the state of the art right now is actually order of r log r for a mixing time of this walk. In particular, one place where you can implement this very quickly, you can take a single step of this walk very quickly, is in the case of spanning trees of a graph. And so somewhat surprisingly, this actually gives a very fast algorithm to sample a random spanning tree from a graph, so uniformly at random. In particular, if you start with something with n edges, then you can approximately uniformly at random sample from this in time n log n squared. This improves on, this is a very classical problem. Before this, the state of the art was close to n. So it improves a bit on the state of art in this classical problem. And just as a concrete example, so the algorithm is if you start with some spanning tree of some graph, then the algorithm that's very quick to implement is that you can get another, the Markov chain on spanning trees of a graph is you could, instead of removing one, you could add an edge, which will form a cycle in this graph, and then remove some edge to get back to a spanning tree. And this will define a random walk in the space of spanning trees of your graph. And so you can walk around this space. I forget how many of these I've done. Let's see. Okay. And the guarantee is that after some number of steps, here about 30, that no matter where you start, any particular spanning tree shows up with about equal probability. And so if you want to sample a spanning tree of your graph uniformly at random, you start anywhere and take about 30 steps in this Markov chain. So on a high level, we used the log concavity of some polynomial, namely the generating polynomial for the spanning trees of some graph, to understand something about some Markov chain, the mixing time of some Markov chain. This has also been generalized quite a lot in the time since. One generalization is something called fractional log concavity. which I'm happy to tell you more about if you ask. But so for whatever a zero locals expander is, we saw that, or I told you that it coincides. The simplicial complexes that correspond to this are exactly independence complexes of matroids. And this theory, developed in the high dimensional expander community, has a parameter in it. And there are examples of simplicial complexes that satisfy this for these other parameters, interesting ones. But in general, the combinatorics of these are not understood. You could fix some any parameter lambda and try and understand what simplicial complexes appear here. And this is quite open. So this group of authors use this theory of fractional log concavity to approximately count and sample from what's called monomer dynamo systems in planar graphs. There's also another generalization called spectral independence, which maybe I don't want to go into too much, but again, trying to understand mixing times of random walks using the eigenvalues of certain matrices that you cook up from this. So maybe I will try to wrap up and just say, so this property of strong log concavity, or Lorentzian polynomials for the aficionados of that. So this is sort of a useful and testable condition. It's testable because because of these characterizations that use small pieces of a simplicial complex or a polynomial to generate the entire thing. It gives a connection between discrete and functional log concavity, which we saw in the beginning. It includes many interesting polynomials, in particular lots of polynomials associated to matroids. And it also has lots of nice implications for mixing times of natural Markov chains on these objects. And so I think that is all I have time for. So I will stop and thank you for your listening. Thanks.
So are there questions?
Thank you for a wonderful talk. I wanted to ask about the fractional Log-concavity. So
Yeah.
could you go back?
Yeah, so
is that a translation of gamma local on simplicial complexes into the polynomial language?
So if you have some polynomial, what you're actually interested in is, for example, half log concavity. You'd be interested in the log concavity of f with, for example, the square root of the variables plugged in. Be interested in the log concavity of this on the positive orthant, as well as its derivatives. You want this to be sort of log concave on the positive orthant. This would be a condition for half log concavity. This is actually what shows up in the sort of monomer dynamo system. So here, this only really makes sense if you restrict to yourself on the positive orthant. But this will give you a perfectly well-defined function from r plus Cn to r. In fact, r plus if you start with a polynomial with non-negative coefficients. And what you want is that the Hessian of log of this function is negative semi-definite everywhere on the positive orthant. And if you have that, then you get some nice consequence. Then if you have this and you have it for like all of its derivatives, this corresponds to a sort of whatever a half local spectral expander is. And so then this gives you something, tells you something about the mixing time of some Markov chain. A Markov chain sort of on the monomials that show up in this polynomial. Does that answer your question? one positive and all 0. Yeah, I think there, so the question was, oh no, you can hear the question. Yeah, I think, what? Rank 1, yeah. Like if you have a, what's the easiest case? Yeah, I don't know if those are the, I don't know if you should think of those as the interesting boundary cases. So to me, the interesting boundary cases are actually, so this, and this is maybe ties in better with the definition that Peter and Jun give for Lorentzian polynomials is so they actually show that the set of polynomials with this property, if you fix a degree and you fix a number of variables, they define an open set where you have all of the monomials of degree d and n variables show up, and then you ask for this property, and they show that so that's an open subset in the real vector space of polynomials, and that when you take the closure of this open subset, then you pick up that this class of polynomials is the closure of its interior, if that makes sense. So I think of the boundary cases as actually ones with smaller support, where like you have more zeros in the actual coefficients. So one can think of these as like matroids, for example, with fewer and fewer bases. So to me, those are the sort of more interesting boundary cases. Yeah. Yeah. Mhm. In the examples, yeah. That's a great question. As far as I know, in general, so I cherry picked my example to be very uniform and very nice. Yeah. So in general, I don't actually know if the eigenvalues are always rational. I would be very surprised. Yeah.
Precisely what you said, or people are interested in other kinds of
yeah, great. So for me, in the example, everything was uniform. Yeah, so I lied a little bit in the details. The probability of adding is not uniform. Yeah, the probability of adding actually depends on what your target distribution is. You have some target distribution you want to sample from. In my example, it was all uniform, and everything was very uniform. So the end. So, but yeah, in general, the probability of adding is going to be proportional to something, and the something is going to depend on what your target sort of distribution is at the end. And the more complicated that gets, the more complicated the adding rates get. Yeah. Mm-hmm. Oh, that's a good question. I personally cannot tell you anything about non-reversible Markov chains. Yeah.
So following up on this, so how does this algorithm compare with other methods for sampling for general matroids?
So before this, there were a lot of sampling methods for specific types of matroids. There's lots of different classes of matroids, and some of them can be sampled from others. But even in the case of spanning trees, which is sort of to me, like the best of all possible matroids, this actually sort of is one of the sort of best sampling algorithms known. And so one of the nice things is that it actually you can do this for arbitrary matroids. Yeah, that's a short answer. Thanks.